My name is Caitlin Bannan. I'm a graduate student with David Mobley at UC Irvine. I spent the summer of 2017 as an intern at OpenEye Scientific, so I'm going to talk about the machine learning model that I built while I was there, and then some results from the SAMPL6 blind challenge. All right, so I want to start with just sort of make sure we're all on the same page about what machine learning is. I'm pretty sure that this robot learning chemistry is what my family thinks when I tell them I teach computers how to do chemistry. But I like Rob Shafire's quote that machine learning is just computer algorithms learning to do stuff. So kind of in popular news, we see that as speech-to-text technology or self-driving cars, but it can also be as simple as just linear regression models. So some of this we've all been doing since we were like 12. All right, so then just an outline for this talk. I'm going to give sort of an overview of what sample challenges are for anybody who's not super familiar with those. And then I'll describe the Gaussian process model that I built at OpenEye, and then the SAMPL6 results from my model and a little bit of an overview. Okay, so starting with just a sample overview. So SAMPL stands for the Statistical Assessment of the Modeling of Proteins and Ligands. But the idea is that you can have these sort of blind challenges to test how well can we do on free energy calculations or other types of calculations in sort of set toy models or set systems where we have an idea about what the right answer is and trying to limit the number of variables where things can go wrong. So historically, trying to test things like how good is your force field, conformational sampling, or chemical effects. So historically, that's mostly been host-guest binding calculations and hydration free energies. But then in SAMPL5, they added distribution coefficient calculations, and then most recently in SAMPL6 pKa predictions. So just looking, the pKa predictions sort of came out of the log D or distribution coefficient calculations. So what those are is a partition coefficient, which is how we're used to thinking about these, is the neutral solute moving between two immiscible solvents. Distribution coefficients are the same idea, but they're looking at all forms of the solute, so all tautomers and protonation states in both the water and the organic phase. And traditionally, even experimentally, you move in between these by using the pKa of the solute, because for the most part, the only change in concentration of the different protonation states in the water phase when you're protonating and deprotonating, which we can then calculate with the transfer free energy relating to sort of the free energy calculations that both the Mobley group and Chodera group have spent a lot of time on. But what we saw in these log D results was that based on the pKa used to correct from a log P calculation into a log D calculation, you saw significant changes, both in the actual predicted log D and significant changes depending on who did the pKa prediction. So they're very sensitive to that initial tautomer choice and the pKa calculated for that molecule. Okay. And this isn't just important for log D, although that's a nice toy system. But if we do the same thing with a protein ligand binding system where you have a different primary protonation state in the binding pocket than you do in the aqueous phase, you have to take into account that thermodynamic cycle and can lead to errors up to 1.4 kilocalories per mole by just an error in a pKa of 1. And many protein binding calculations claim that they can get within 1 kilocalorie per mole error. So obviously an important part of that, of other calculations that our groups do. Okay, so I'm going to focus more on what model I built and what our goals for that were. Okay, so I started at the beginning of the summer with a list of what do we want out of this model. If we're going to predict pKa, what are our goals? So the first one was a bit contentious with me and my mentor. My goal was to have just one machine learning model regardless of what molecule you gave it. So that the most popular and successful commercially available models for this build separate machine learning models by functional group. But I was insistent that if we describe the right physics of the molecule, it shouldn't matter. Okay, so then, which leads to, we wanted features that were physics-based and not just sort of arbitrary things. And that it needed to include some kind of prediction of uncertainty or domain of applicability. So it should know if you give it a molecule that's completely outside its training set, that it's not going to do well on it, should be able to predict that also. Okay, so I'm going to walk through how we assign protonation states and then how you translate that into a set of physics-based features that will be fed into the model, and I'll describe the model that I chose to use, then look at some actual data. So identifying ionizable groups was entirely heuristic. So we decided what we thought was acidic and what things we thought were basic, identified where they were on the molecule, and then protonated or deprotonated it depending on which one was identified. So we're looking at both the protonated form or the acidic form of the molecule and the basic or the deprotonated form. So what I'm showing here is just some fragments that are examples of things that as chemists we would obviously think are acidic and basic. It's not necessarily a complete list of what was used. Okay. So then in deciding what features to use, our thought process was what, as a chemist, if I'm going to guess what a pKa is, what things are we thinking about? Like what are the physical effects that change how ionizable a molecule is? So that's things like resonance and inductive effects, and then sterics and solvation around the ionizable group. So we translated that into physics-based features and decided that we were willing to have a slightly slower model than the kind of go-to QSARs in exchange for maybe having a more physical description of the molecule. So translated that into partial charges, which we used AM1BCC for, solvent accessible surface area of the ionizable group, and then solvation free energies using OpenEye's Poisson-Boltzmann model, so a fast free energy estimate, not where the difference is between the protonated and deprotonated forms. And then Weiberg bond order on the ionizable group and differences in AM1 energy. So technically during the summer, I tested a random forest model and a Gaussian process regression. I'm only going to talk about the Gaussian process regression because it performs statistically better the whole time. So the other word that you might have learned this as is kriging. So kriging was created by geophysicists in South Africa to try to find gold. And essentially it's a distance-based metric. So the idea being that if I have a slot where I know there's gold in this case and slots where I know there's not gold, you can use an unknown site and the distance between them to try to make a guess at what the probability of it being positive. So what we're looking at in this case is distance in that feature space, not distance in, like, not just 2 dimensions like they were. And it's handily implemented with scikit-learns. We didn't need to write our own model. All right, so another way to think about these, not entirely mathematical way of thinking about them, but to give a little bit of a better picture of the way to think about Gaussian processes, is that they're a distribution of functions. So I think most of us are used to thinking about distributions in sort of like one or two dimensions, right? So we can imagine saying I have some sort of prior where this black line is at the n equals 0 for people who can't see me pointing. And then as you add data, seeing the shift, if you can imagine, we put more data closer to the 1 and the distribution moves. So what that looks like in more sort of function space is you can imagine we have distance in your feature space on the x-axis, and the initial prior is just a bound where you say, this is where anything could be, so it has an inherent kind of, this is the range, and then you're pulling out functions. So instead of pulling a point, you pull out any kind of nonlinear shape. And then once we add data, your posterior instead looks where you have a limited number of curves that actually go through your data or go near your data, but an inherent uncertainty in the areas where you don't have the data well defined. Okay. So I'm going to apologize for the quality of this graph. But the idea here is to check if that assumption in distance space is a good one for our model. So do our features in distance space actually make sense for pKa? So what's being plotted here is distance on the x-axis, and then to get the points on the y-axis, we have pull all of the data points that are within that distance and take a variance in the experimental pKa. So that's what's making these blue dots. And then all of the other dashed lines are different types of kernels that can map, that are mapping distance into a predictive pKa. They're just sort of estimations of the shape of those kernels. They're not a actual fit kernel. But the idea here is just if we're at low distances, we should see very low, relatively low variance, and the longer distances we get to very high variance. So we've walked through how to identify ionizable groups and what features were calculated from both the protonated and deprotonated forms and which model they were being plugged into. So we can look at some actual pKas and what we were training on. So OpenEye has a relatively, on the scale of computational chemistry, relatively large data set of small molecule pKas. So I started by just removing things that are sort of outside the range of biologically relevant, so measured only from 20 to 25 degrees Celsius and actually measured in aqueous water solutions, not something else. So that led to about 26,000 data points, which is only about 10,000 molecules. So either due to repeats in the repeat measurements on the same molecule and molecules that have multiple protonation states. So then to start, I isolated only molecules with a single ionizable group as a way to have sort of a toy-ish set, reasonable set, but one where we more thoroughly understand where's the ionizable group and how to map that one point into an experimental pKa. And then I separated that data into an internal test set, so I took out 10% as sort of an arbitrary percentage, but enough to have something set aside that I didn't look at, the model didn't see throughout the summer. And then I split the rest of that training set into what we call 3 cross-validation sets. So what that means is while I was working on building the model, we would train on 2/3 and test on the last third. And then you rotate as a way of checking that you're not overtraining, because you should get approximately the same error regardless of which 2/3 you train on.
How did you do the training test split? Based on time, based on scaffold, based on random? Just curious.
Yeah, so I signed essentially like an integer experimental pKa and then randomly split where that was evenly distributed, with the assumption that that would sort of get in close to even distribution of the chemical space. So just to start, I have an example validation set. Once again, I apologize for the quality of the graphs. I don't have the raw data, so I can't make them better. And then that internal test set. And the main thing that I want to take away is that the sort of error metrics are about the same on the internal validation and the internal test set. So it at least shows that we're not overtraining the things that we're working with.
Pat would yell at you.
Who? Pat?
And our squared confidence intervals.
Oh, yeah. So I am not showing the error bars on the R squared because it comes out to like 0.0001 when I was bootstrapping. So it ended up.
That's good.
To some extent, not quite being worth showing, although I have them.
Out of curiosity, what was the R squared on the training set?
So I don't have the slide in this slide deck, but they were on a similar. They're on a similar scale. So the RMSE I think was slightly lower, but the R squared was similar. The main takeaway is that we have similar values. I don't. Once again, things that I wish I had on the slides. I don't have those sort of, the two that have very large error bars and are in the same space. I don't have the pictures of the molecules, but I remember them being things that were sort of out there. So we're not necessarily well representative of drug molecules, and certainly probably were not functional groups in the training set, or like functional groups near the thing being protonated were different than what was in the training set. Okay. So I said that we wanted to be able to assess uncertainty or domain of applicability. So one way to do that is with a QQ plot. I'm going to attempt to walk through how this is plotted for anybody who's not used to squinting at them. So what the idea here is that you're saying that if our predicted values near sort of a normal distribution, then we're doing a good job of predicting. If the uncertainty nears a normal distribution, then you're doing a good job of predicting uncertainty. So on the x-axis, we have the percent of data that falls within a certain number of standard deviations of a normal distribution. So if you're at 1 sigma, you have 0.68 on the x-axis. And then on the y-axis, you have the percent of your, fraction. Yes, they're not percentages, they're fractions. You have the fraction of your predicted values that fall within that number of predicted uncertainties of the experiment. So how, at the 0.68, on the x-axis, you have how many of my predicted values fall within 1 error of the experimental value.
This is awesome, by the way.
Yeah, so I will say,
really
for those of us who are used to looking at QQ plots for things like hydration-free energies, where people are really bad at model uncertainty, this looks amazing. I think in the machine learning world, with models that are used to predicting uncertainty, they tend to be a bit cleaner. Okay. So essentially what we're saying is we did a pretty good job of predicting uncertainty. However, remember all of the data I've showed you so far is only on molecules with a single ionizable group. Things are about to get more messy. All right. So, however, we could use this same way of predicting single deprotonation and then propagate that through into macroscopic pKas for molecules with more ionizable groups by just using thermodynamic cycles and sort of basic rules from pChem. And this 2, protonation state site is pretty common. Probably some of us somewhere along the way in undergrad looked at it. Or it gets more and more complicated the more ionizable groups you have. So I have the equations for 3 there. We have it propagated out to up to 4 ionizable groups, but I won't show how messy that got.
But it's even worse. Like the macro pKas and those you compute are not going to be the same if they're close to each other.
Right.
They'll just be totally crazy.
If the microscopic are close to each other?
Even if these macro pKas are close to each other, when you get them from a fit, it's very hard to resolve exact values.
Right.
So
Yeah.
do you also do this for tautomers as well?
Right now we're not. So that certainly adds another level of complexity that at this point we're not basically just ignoring, which is not ideal. So to get the initial tautomers, which direction did that start at? It's starting at the neutral one, which is not ideal. We did do an initial, are we getting a reasonable close to best? I mean, people getting best tautomers is not a thing that's well understood, so I wouldn't put that at any level of confidence, but at least are we starting with a reasonable tautomer using some of OpenEye's tools?
Got it.
Single tautomer protonation
And
state.
yes, it only started with a single tautomer for everything, which is another
Got it.
level of uncertainty. That being said, on most of them where it's a single ionizable group, that's a little less concerning because there's less things like nitrogens that cause variation in tautomerization.
Yeah.
All right. So in an attempt to try to expand that training set a little bit before SAMPL, so we took that initial, there's about 2,400 data points of single ionizable groups after taking out that test set. And then we added diprotic molecules where the experimental pKas are greater than 3, and we felt confident identifying which order they went in so that you can treat them as essentially two single ionizable steps as a way of expanding the data set to at least include some Zwitterions and some slightly more complicated combinations of functional groups. So just fed that in as single ionizable groups into our model. All right. So we have SAMPL6 data that was a blind challenge asking for macroscopic and microscopic pKas for a set of, there's 25, right? Yeah, 25. Kinase inhibitor-like molecules. So these really more thoroughly represent sort of drug-like space and all have, or almost all have multiple ionizable groups. Apologize, they're a little bit small. Okay, so then the SAMPL6 organizers asked for potentially three different types of data or predictions. So type 1 was just a microscopic pKa, so removing a specific hydrogen. Type 2 was populations of microstates at different pHs. And then type 3 was the macroscopic pKa, or the removing of any single hydrogen, including all of the states. And we were instructed to include anything that your model predicts. So you could go outside the range of what was actually experimentally available. Okay, so I don't have populations of microstates. I guess we could have tried to propagate that from our predictions, but we didn't. But I inherently, in predicting microscopic pKas and then propagating them through that thermodynamic cycle to get macroscopic, so we reported both. But I'll start with macroscopic pKas because we have experimental data on all of the molecules for that. Okay, so something that was maybe not obvious to some of us to begin with was that just the mapping of predictions to experiment is a lot less intuitive with pKa than it is with something like hydration-free energies, where everyone's only reporting one molecule or one value for every molecule. So there were a few different attempts to try to map predictions to experiment that the sample organizers used. So one was to just say, we're just going to map the predictions to whatever the closest experimental pKa is. And then, but if you have cases like this one where two predicted values are closest to the same experimental value, then one of them just gets removed. So you only keep the one that's closest. So that's not quite ideal. We'd like to at least evaluate both predictions that were submitted. So the second one was using this Hungarian algorithm where instead do a match that allows for the smallest error in the total match on every molecule. However, in this case, you would end up with them crossing. So you're matching the lower predicted pKa to the larger experimental one. Or with pKas, they really should stay in order. So an ideal case would be a little bit more to stick with matching that reduces the error, but keep them in the order that they're submitted. According to Maytab, who was in charge of most of this analysis, that crossing doesn't actually happen very often. We just had an example where it did. And I looked by hand at my data and it never happened. So I'm going to focus on the Hungarian algorithm. I think it's more fair than the closest and didn't require me to write my own matching.
And I think it's the minimum sum of squared errors, right? Not the minimum absolute error, because
Yes,
you can never have
sorry.
crossing if it was the
Yeah,
sum of the
yeah,
errors.
yeah. No, yeah, sum of squared errors. Sorry. Yeah, okay. So just to give an idea about how people are doing predicting pKa in general, this is a distribution of RMSEs for different participants. So the x-axis is just participant ID, it doesn't really matter. But one thing to point out is that even these people that are like very close at the top are still only at about 0.75 or so error, which is maybe higher than we would like in a world where we're trying to use this to predict pKa of a molecule. The point of putting the GitHub link up there is that it has all of the analysis to do these and has these plots for other error metrics than just RMSE. I just think RMSE is easy to understand. If I remember correctly, those three top ones are at least in the top three across most of the error metrics. So the first one is from an academic group that has a pretty well-established QM calculation, but they include a linear regression as a way of getting the hydration free energy of the proton, despite that being a value that's sort of known. So it's a way to correct for potentially issues with solvation, with solvent models. And then the other two are commercially available products, Simulation Plus and ACD Labs. Simulation Plus claims that it has somewhere around 1 million data points where it's training 10 separate neural networks with 100 descriptors, at least 100 descriptors.
They have a lot of data.
They have a lot of data. I don't know what's in their descriptors. It's not public. And then ACD uses Hammett type equations where you look at sort of reference molecules and then the effects of different functional groups around them. So again, there's probably more to it than that. I don't have all of the details because it's a commercial model. All right, and we're over there. I do want to point out that when you consider the error bars on the RMSE, pretty much like the middle 15 at least are really hard to distinguish. So
you may have to go to real chemists too and have them guess.
No, so there's no real chemist guess. There's Jeff and me guessing.
Okay, all right.
So OpenEye has a tool called pKa Prospector that does a database lookup based on substructure. So I just used that raw and then sort of made a best guess of the things it gave me and just submitted numbers with a error estimate that was like, this is how much I think this looks like the molecule.
So the Gaussian process. Do you know which one that is?
I know that I think mine was slightly worse than the Gaussian process, and Jeff's was like somewhere in this middle block.
Okay, but they were essentially statistically.
They were like statistically.
Your Gaussian process is fully automated and gives you very good error bars.
Yes, doesn't require a human to squint at molecules.
So it's effectively good as a.
Well,
Jeff
I think it would be I think it would be worth having a med chemist who probably does this a little bit more than Jeff and I do it to get a more reasonable guess.
But statistically
Gaussian process. Okay, so I highlighted values based on our predicted uncertainty, mostly because if you told an experimental chemist that you knew the pKa of their molecule within ±2, they would just be like, well, you probably don't know the pKa. Which is fine. I mean, it's a good thing that the model knows when it doesn't know. But that's just for visualization effects. And I mean, we have the error metrics. They're not great, but they're not horrible. So I want to start by just looking at a couple of examples where we maybe didn't do as well. So on this one, we remember that identifying ionizable groups was entirely heuristic. We made the choice to never identify amide nitrogens as either acidic or basic. So in this case, we only identify these two nitrogens, and we give a +2 to +1 on that, on our predicted one at about 1.7, and then +1 to 0 at the about 4 value. And we think it's relatively likely with the amount of conjugation there that nitrogen might be acidic, or at least maybe could be being deprotonated around 12. We think it's highly unlikely that +1 to 0 should be a 12. Regardless.
Yep.
So,
but isn't that an amide bond that forms between the CO and the NH?
Yeah. Yes.
And you think that could be possibly titratable?
I I think it is more, I don't know that I think it's titratable, but I think it's more likely that that's titratable than the other two nitrogens deprotonate at 12.
Okay.
Right? Like they're not, the dominant state in those is going to deprotonate much lower, right? So like,
That's also,
I don't know if it's like a feature of the experimental data or if that is really being deprotonated or if, yeah. But that,
okay.
that was our best guess at what was happening at 12.
Okay.
There's some, I don't remember the group off the top of my head, but there is some experimental data supporting that if they're conjugated enough, those nitrogens can deprotonate relatively low, but it's not usually as low as 12. It's somewhere around like 15.
Right, right.
So it's still a stretch, but it doesn't make any sense for it to go from +1 to 0 at a pH of 12. Okay, and so that group was relatively well represented, and the big point there is just that like we're not getting the uncertainty isn't matching up with the air there, but it largely, so not necessarily to say that we think that scaffold is contributing to the ionizable groups on the other ones, but we do think there's something going on at the more major outlier. Okay, so the other thing that happens that you don't see in that nice x equals y plot is that we're reporting all of the protonation states regardless. Regardless of if they're in range or out of range or if they happen in the right order. So for example, with this molecule, we predict that it happens at 5 and then 3 and then 7. Not really physically relevant, but there's only one experimental value, so it just matches to the one that's closest and might sort of make our data look a little bit better than it actually is. However, all of those errors are really big. So mostly it's just telling you, I don't know the pKa here. Okay, so then how do we, right? Basically the takeaway being like, it would be great if we had experimental microscopic pKas, those can be hard to get, or at least something about, can we know if that experimental value is the +3 to +2 or the 2 to 1, etc. So like that we at least know where to pair them. Okay. And then really, as we've sort of talked about this whole time, there's a lot of unfamiliar and polyion and polyprotic molecules in the set. So for the most part, those large errors are a good thing, because it's saying they're outside of our training or outside of our domain of applicability. Okay. So we can look at that QQ plot once again. So this looks pretty good, right? We're close to agreement with a normal distribution. And then one way of assessing sort of, is it the predicted uncertainty that's good, or is it just like any uncertainty would have been okay for this set? You can say, what if I just did the thing that a lot of people do, and I take the RMSE from an internal test set and assume that the uncertainty on every single data point is the same as the internal test set RMSE or some other error metric. So if we just set them all to about 0.75, we see less good agreement with a normal distribution. So that's promising in that we're actually making predictions on our uncertainty in a way that's useful. So I'm going to go over just the few data points that we have for the microscopic pKas for experimental data. So Maytap or someone at Merck, I don't remember who actually did the experiments, ran a couple of NMR experiments to see what the microscopic pKas were. So one was with this scaffold where there was only one identified microscopic transition and it directly paired with the experimental macroscopic prediction. So they made the assumption there's 5 other molecules with this same scaffold with some other groups coming off. So they made the assumption that the macroscopic pKas can be used as the microscopic measurement for that same nitrogen. So that gives us 6 data points. And there was a second molecule that had 2 experimental values for the macroscopic data that also with NMR experiments line up with microscopic pKas on those 2 sites. So that gives us a way to actually look at some of the microscopic predictions. And once again, for the most part, those error bars just sort of say, these are mostly outside of our domain of applicability. I mean, there's some sort of, like they're at least somewhat good agreement on the correlation, but I think for the most part, the error bars are high enough that really we just don't know. All right. So there's some good lessons to take away from SAMPL6. So the first one being mapping or matching with predictions and experiments was easier said than done, but I think we've found at least a method that works for automating that. for everybody to be able to look at it. For our model, we need to probably expand the definition of ionizable groups. Oh, I took that slide out. There's some evidence that we probably need to be looking at either multiple tautomers or taking into account tautomerization at the different charge states. And that really, more importantly, we need to get polyprotic molecules into the training set. So the main reason I didn't do that in the 15-week internship is that I was using scikit-learn just out of the box, which expects that you give it a list of features, it makes a prediction, and it has a one-to-one match with some sort of experimental or training value. Except if you have multiple ionizable groups using the same metric that we're using here, we have 4 predictions that only map to 2 experimental values. You would have to write a new cost function or use a different model that allows for more complicated mapping. Okay, so I think probably with this audience, we're all very convinced that pKa is important, both in even just simple calculations like partition coefficients or distribution coefficients, but more importantly, in things like protein binding. I showed you the machine learning model that I built at OpenEye, which we think is, while predicting large errors, is at least doing somewhat good and could do better if you're able to push it into doing a better job of predicting microscopic pKas when you have multiple ionizable groups. All right, so just to acknowledge people, none of these challenges would be possible without all of the organizers and participants putting in lots of work, and all of that stuff is available publicly for both the log D and the pKa challenges on GitHub. And then this is my group in Irvine, a little bit of an outdated picture. And then my mentor at OpenEye, Jeff Skillman, and funding from OpenEye and Mulsi, etc.